In a previous video, we saw that if you have a wire or some elastic band, say of length L and some cross-sectional area A, and if we stretched it by some length delta L, then a restoring force gets generated inside the wire. This force tries to restore the wire back to its original shape. That's why it's called a restoring force. And from this, we define two new quantities. One we call as the stress, which we defined as the restoring force per unit area. Stress is the quantity that tells us how quickly the material tries to snap back to its original shape. And the second quantity was strain, which is the change in length per length or relative change in length, which tells us how much the material has been deformed. And if you're not familiar with this, or if you require a refresher, it would be great to go back and watch that video and then come back over here. But what we want to do in this video is to find the relationship between stress and strain. All right, so let's do that. Now, one thing we could intuitively say is that if you were to increase the strain, that means increase the amount of deformation you produce, then the stress in the material would also increase, right? I mean, if you deform it more, the material will try to snap back even more. So more strain should produce more stress. Makes sense, right? And guess what? Experiment supports that. In fact, experiment tells us for small strain values, stress is even proportional to strain. What that means is if you were to double the value of strain, stress will just get doubled. Linear proportionality. And this law, which says stress is proportional to strain, is called as Hooke's law. Hooke's law. But this law has a limitation. Remember that if you take a spring and if you stretch it too much, then it will not come back to its original shape. It will have permanent deformation. So Hooke's law is only valid as long as you don't strain it too much. All right? And so we usually say this only works within the elastic limits. Within elastic limits. And every material will have its own elastic limit, but there will be some limit. So as long as you're within that, this proportionality holds. And now we can go ahead and replace this proportionality with an equal to sign and put a constant over here. And what we'll do is we'll try and understand what this constant is really telling us. All right. So let's throw some values of K and let's see what happens to stress and strain. If we start with very low values of K, so let's say K is very close to 0, which means very low value, then notice that for a given strain, stress will also be very close to 0, right? And what does that mean? Well, just imagine if you have a wire which K equal to 0, and if you strain it a little bit, but you find that the stress is 0, that means if you let go of it, the wire doesn't come back to its original shape. Does that make sense? Which means that if K is close to 0, then the wire or the material has a very low elastic property. Makes sense, right? So K equal to 0, very low values of K, which just means low elasticity. Low elasticity. And what if we have a very high value of K? What if K is very high? What does that mean? Well, if K is very high, then even for a small amount of strain, the stress would be very high. Which means if you take this material and strain it even a little bit, the stress will be very high and it will snap back very quickly to its original shape. In other words, it is very highly elastic. So high value of K means highly elastic. So can you see that K is actually telling us how elastic a material is? And it's for that reason K is called as the modulus of elasticity, or we just call it as elastic modulus. Elastic modulus. And it just tells us how elastic a material is. Higher the value of K, more elastic the material. And what's the units of K? Well, since strain has no units because it's length per length, centimeter cancels, K should have the same unit as stress. And the stress will have a unit of newtons per meter square. So K will also have units of newtons per meter square. And guess what? There are different ways in which you can deform a material. For example, you can take a wire and stretch it, or you can even bend it, or you can twist it, and so on. And so for different kinds of strain that you're going to produce, the poor material has to produce an equivalent kind of restoring force and so an equivalent kind of stress. So for every kind of strain you produce, there will be a corresponding stress that will be generated. And for each of these stress strain pairs, Hooke's law works. And so for each kinds of stress and strain, we will have different kinds of elastic moduli. All right. And now we'll talk about one particular kind of stress and strain. So let me get rid of this. And for whatever follows, please just remember Hooke's law, that stress is proportional to strain. All right. So the kind of stress and strain we're going to talk about, to understand that, let's look at an example. Imagine we have a cylindrical rod that is connected to a ceiling on one end, and it has a length L. Now what we can do to this rod is we can start pulling on it. Say we can pull on it this way. And when we do that, the rod gets stretched. So delta L is the amount by which the rod is being stretched, and this produces a strain, delta L divided by L. And now the rod will try to undo this by generating a restoring force to bring it back to its original shape. And the restoring force now will be in this direction. And just like when you take a string and you pull on it, that we say that the string is under tension, similarly the rod which is being pulled now is under tension. And so now if you calculate this restoring force, divide by the cross-sectional area, divide by this cross-sectional area, the resulting stress now is called as tensile stress. So we call this as tensile stress. And this strain, delta L by L, we call that as tensile strain. Now another thing you could do to our rod, so we take that same rod, another thing we could do to this is instead of pulling, we can now push on it. So this time, let's push on it. And when you do that, the rod now gets compressed. So again, notice a strain is generated, which is delta L by L. And because of that, now the rod will try to undo that, will try to bring it back to equilibrium by generating a restoring force in the opposite direction, this way. Again, if we calculate this stress now as the restoring force divided by this cross-sectional area, then we call this stress as compressive stress. Compressive stress. Again, makes sense, right? Because now the rod is being compressed. So compressive stress. And this strain, that is resulting strain over here, is called as compressive strain. And together, this tensile and compressive, we often call it as longitudinal stress or strain. And the word longitudinal comes from the fact that we are talking about stresses and strains happening along the axis of the rod. So it's also called as axial stress. That's another name that we give to this, axial stress and axial strain. Another thing to notice is that this restoring force in both the cases is perpendicular to the area. Can you see that? It's perpendicular to the area of cross-section. And therefore, the longitudinal stress is also sometimes called as normal stress. Normal, because normal stands for perpendicular. It's telling us that the restoring force is perpendicular to the cross-sectional area. There are some symbols used over here. So when you calculate the stress, the restoring force divided by the cross-sectional area, this longitudinal stress or normal stress is usually written by the symbol sigma. And similarly, if you take this strain, that is delta L divided by L, relative change in the length, remember? Then this strain is usually represented by the symbol small Greek letter E, epsilon, it's called. And now if you use Hooke's law, we could say that this stress is proportional to strain. Proportional to strain. And so that proportionality can be written as equal to, and one elastic modulus comes over here. And this elastic modulus is often written as Y, and we call that as Young's modulus. Young's modulus. So the thing to note is whenever we have the restoring force perpendicular to the area, we call that as the normal stress or longitudinal stress. And whenever we're dealing with longitudinal stress or strain, the modulus of elasticity that we need to use is called as the Young's modulus. Now, one last thing we will do is look at a couple of real life examples where we can see tensile and compressive stresses. Well, when it comes to tensile stress, this picture comes to my mind. Notice that this is a wrecking ball which is used in demolishing buildings. So it has a lot of weight, and it's being hung by some steel wire or a chain. And notice the ball starts pulling on this wire, which causes a tensile stress over here. So if you want to calculate how much strain gets generated or something, then we are going to use Young's modulus over here. Similarly, for compression, the picture that comes to my mind are pillars. Any pillars that we use in any construction, notice that it's under compression because the stuff that is coming on top of it is pulling, or it's pushing down on this, and the ground is pushing up on it. That's causing the pillar to be compressed. And due to this compression, there will be a stress and there will be a strain. And so again, if you want to calculate any of those, then we are going to use Young's modulus for that. Now, in general, the Young's modulus for tensile and compression need not be the same. A material could be more elastic when it comes to tensile, but less elastic when it comes to compression. And therefore, you might have two different values in general for Young's moduli. However, in any problem, if they don't mention those two different values, if they just give you Young's modulus, then you can use that number for any one of them, tensile or compressive.